Good evening for everybody. First of all, my gratitude to the organizer of this conference, which is dedicated to Volodya Buslaev, a remarkable mathematician, outstanding person, and last but not least, one of the best my friends. Unfortunately, he is not with us. The subject of the talk was partly motivated by discussions with Volodya, and this is about the asymptotic analysis of the quantity written here, which is important in getting more and more important in a number of fields of physics and related. And the quantity entanglement entropy is not simple to define and even more simple to study. And as usual in these cases, people start from simple, so to say, toy models. And one of those models is free fermions, which are closely related to spectral theory, which many of us, we know a lot, we worked a lot. And this is why I choose the subject. And this is the outline of my talk. First, I'll explain what is the entanglement entropy. Then I'll refer several results, mostly by physicists, not proven. And then I'll describe the model which I'm going to discuss, and then the results of myself and other people related to the asymptotic analysis of this model. Well, excuse me. And let's start from definitions. And first is a bit of advertisement. Entanglement is a quite complex and delicate quantum phenomenon found by Einstein in 1935 in negative sense. In fact, Einstein was occupied by constructing a counterexample of quantum mechanics. And he discovered entanglement as a way to show that quantum mechanics is false. And the very same year, Schrodinger showed that it is not false, quite opposite, it's quite useful. And now people now know that mostly since the 80s, that mostly first were Deutsch and Feynman, discovering that it is quite serious resource for quantum computing. But let's start from the quantum mechanical definitions, quite simple and general. So you may know that quantum mechanics describes the state of the system as a positive via the positive definite operator rho, which called density matrix. It's positive definite trace one operator. Then there is a particular case of state is just when the density matrix, just the rank one projection on a certain vector of norm one. It's called pure state. If it is not pure state, it's mixed state. And then next is important notion is a composite system consisting of two subsystems. And what does it mean composite? That means not always, but quite often, that means that the state space of whole the system is a tensor product of spaces of the components. Yes, and then the main definition is we say that the state, pure state, that is a vector of the tensor product is separable if it is tensor product of the vectors from the factors, tensor factors. Otherwise, we say it's entanglement. For those who know a bit of probability, I would say that these notions, separability and entanglement, are somehow analogous to the notion of independent random variables. Yes, and a good example, quite famous for many reasons, is called Bell state. You take these are maybe you do not know, these are so-called Dirac notations. It's just a vector of your Hilbert space. Take the simplest case when the dimension of both space is 2. This is the quantum system with the dimension 2 is called qubit. Yes, we have 2 qubits. We have the basis in the whole spaces, and we construct the vector, which is already in the tensor product. Very simple, just tensor product of basis vectors plus and minus. And it is easy to see that this vector can be presented as a tensor product, therefore it is entanglement. Yes, and the entropy, yes, the word entropy is quite, I know, quite taken. There is a lot of object in physics and in information theory, in mathematics, etc., with this name. But I just would like to stress the notion that in almost all applications, classical, not quantum mechanical, and the entropy means something that characterizes the lack of knowledge or somehow the amount of randomness that you possess. In quantum physics, it's also in a way the quantum the measure of quantum randomness. And the measure, so it was in classical physics, it was introduced by Boltzmann, Gibbs, Shannon, Kolmogorov, a lot of people. In quantum mechanics, it was introduced in the 30s by von Neumann, and this is its definition. You have a quantum system, which is described by the density matrix rho. I remind you that it's a positive definite matrix of trace 1, and the von Neumann entropy is defined by this formula. Yes, and its important property among many important is that if you have if rho is if your system is its state space is dimension n, then the maximum of entropy is a log of 2. There is an analog of this assertion in classical physics. In fact, this belongs to Shannon. Well, and then there is a quite important notion. Assume that you have this composite system consisted of 2 components, and you have rho s is its density matrix, and you introduce the object with its own reduced density matrix. So I remind you that in many cases, in particular, if your state space, like it was in the previous transparency, was a tensor product, you can introduce the so-called partial trace. Just, okay, there are many definitions, but believe me, all of them more or less, I know, useful and equivalent. So if you trace out the degrees of freedom of system B, of subsystem B, then we are left with the system A, and it is its density of states. And again, for those who know a bit of probabilities, quite close quantum analog of marginal distribution. You have, say, 2 random variables, generally dependent. You would like to know the probability distribution of one of them. You integrate over the second one. And this is analog, yes? And quite often in applications, the whole system is in a pure state. It is a rank 1 orthogonal projection on a certain vector, yes? And then you construct the entanglement entropy in this way, as I said, entanglement entropy of the, you take the reduced density matrix and you apply the von Neumann formula. There is a very simple and good example. Take, for example, as a psi, as a state of your system, whole system, the Bell state, which was on, on the previous of this very simple thing. You trace out the degrees of freedom of B. So you, since it is pure state, for any rank 1 projection, the entropy is 0, because in that case, the eigenvalues of rho is either 1 or 0, entropy is 0. But so the entropy of the whole state is 0, but the entropy of the entanglement entropy is 1, so it is maximum. And this is why the entropy was taken, entanglement entropy was taken as a measure of entanglement. and the jargon of quantum information theory is that it's called entanglement quantifier. So we conclude the entanglement entropy is a good, not bad, entanglement quantifier of this property entanglement. Well, let's now you know in my previous examples my system consisted of 2 qubits. Now I usually a qubit physically implemented, for example, as a spin. So you have 2 spins, but now I would like to consider a system of very many spins, 10 to 23. So I would like to consider a macroscopic system, also divide it in 2 parts, and but now I assume that the whole system occupy very big domain omega, yes, of say just a cube, but very big size M script. And now I would like it's a system to be living in certain subcube. So it is lambda living in a smaller cube, and I construct the reduced density matrix of the system A, which I will denote from now on not rho A sub A, but rho sub lambda, and it corresponds the only. So I am interested only what is going on in subsystem. I am not interested what is going in the whole universe. Only in my flat when I am here. And there is a problem. Usually omega, I repeat, M script is quite big, and M is not so big. Therefore, physicists used to write in this case in this way, but how could we formalize being a mathematician, mathematical physicist? What do? We take this construction, we keep M fixed, and we carry out the limit n to infinity. We obtain, as a rule, not always, but usually we obtain quite well-defined quantity, which now depends only on lambda, which is finite so far. That means on M. And we are interested in the asymptotic behavior of this quantity as M tends to infinity, or say the size of this subcube L. Well, and just a little list of people were occupied by this, and what do? Mostly they mathematicians, they are physicists. So the person who introduced this quantity studying by the way, black holes was Bekenstein. Then Hawking made a lot. Then there were people doing something in quantum field theory. There were people doing something in quantum statistical mechanics. There were our friends Korepin and Itz doing models, some models, simple physically, but quite not simple mathematically models, so-called quantum spin chain. They found a lot of results, as I said, partly rigorous, partly not, and indicating that this sign means that I am just saying order of magnitude. Not always it is possible to find that it is asymptotics, but quite often you can find a constant here, but I just would like to show the scaling. So they found that in many cases, both physical and modeling, the entanglement entry behaves like so it is just a function of L. It behaves asymptotically as the real law of lambda. But sometimes it behaves a bit differently. There is an additional factor, log L, and we say initially people were quite surprised, and it was called violation of area law. But since now we, according to the slogan in the United States, think positively, many people start to call it enhancement of area law. Well, it depends on the taste. And now several remarks concerning these results that I just mentioned. So it was a feeling which was derived from the many numerics, heuristic arguments and some model calculations that area law is valid for many body system, interacting system, when you have a gap in their spectrum. But it is still not the spectral theory which we used to do. I mean, differential finite difference operator. It is just, Schrodinger operator or partial difference operator with 10 to 23 variables. So quite serious thing, but nevertheless, in many cases, there is a gap in its spectrum, and in that case, people found that you have the area law is valid. And as for violation of area law, it was, I repeat, it was heuristically found in many cases, but more or less rigorously, it was found in explicitly solvable models, like I mentioned before, one-dimensional spin chains. And if, as for multidimensional case, the only, more or less, only the case in which some multidimensional results we are able to find, it was so-called free fermions, because maybe you know that even free fermions, that means they do not interact. So it is just electrons which, as we know, interact with respect via Coulomb interaction, but we forget for the moment that they just free particles. But since they are fermions, that means that their eigenfunctions, their wave functions, the solution of the Schrodinger equation of 10 to 23 variables, antisymmetric with respect to transposition of any variables. But we are solving this very, very multidimensional Schrodinger equation without interaction, just sum of Laplacians. And these are free fermions, yes? And if you just think a moment, as I said, since your eigenfunction solution is antisymmetric, it can't be tensor product. So fermions, physicists used to say that fermions are always entanglement. And this is toy model which happened to be, available for rigorous analysis, which I am going to present you. So I omit some calculation which requires, some knowledge of second quantization, etc. It's just, I would like to present you the final result. So let H be a self-adjoint operator in just L2 ZD. Symmetric operator, for a finite difference operator. Physicists call it one-body Hamiltonian. And it is Hamiltonian that, in fact, determine the behavior of 10 to 23 fermions because they do not interact. But this is usually simple operator, not simple, but familiar for us operator. And you take this operator and you construct the function of this operator where NF, it is famous Fermi distribution, which is just this function, you see? So it is exponent. If there are two parameters, these parameters E is called Fermi energy, T is called temperature, and if temperature is positive, we have this expression. So it tends to 0 when E tends to plus infinity, to exponentially to 1 when E tends to minus infinity. But if temperature equals 0, and would like very much this case, as you'll see, it contains a lot of interesting situations. After all, noblesse oblige, I am from the Institute of Low Temperature Physics. I have to be occupied by that. So, and the parameter E usually has to belong to the spectrum of my H, and T, as I said, the non-negative parameter. Yes. So we have well-defined operator which acts in L2ZD, and then we take the cube, usually centered at the origin, does matter in fact where, and we construct the restriction of K to this cube. Therefore, we take this matrix, double infinite matrix, which is operator in L2ZD, and you just cut everything outside of the cube. And you get as a result definite matrix, in one-dimensional case, just 2m plus 1 size, yes? And this is the result of my second, not mine, but myself also, but there are many people who calculated independently. So the entanglement entropy of 3 fermions confined to the cube lambda of that form is given by this nice formula. So you take your operator H, it is given. You construct this function of operator, you take restriction, and then you take function H written here, and one more function, and then the trace. So it seems a bit either artificial or too involved. And just to show that it is more or less natural construction, which in fact we know, many of us know, and very many of us heard about. And let me show you some general scheme which includes this one. So let's consider the triple. Yes, the space L2, little L2 or capital L2, and some self-adjoint operator Q, which we call basic operator, and 2 functions. Function A, which acts from the spectrum of Q just to real axis, and the second function that acts from the image of under A of the spectrum to again to the whole real axis, and we call this basic operator. This is our symbol. This is 10 function symbol. It is taken from pseudo differential operator, Steglow's theorem. There are many domains of math where we use the simple test function. It is mostly from statistics, and let's construct these things as that. So we take Q, we calculate the operator AQ. We take its restriction and take phi, and this trace. So evidently, this is just a general thing of which the previous one was a particular case. Oh, excuse me. Particular case written here. Here our phi is H quite concrete. Our A is again absolutely concrete, but there is general scheme. And to show you the general scheme in the problem written here is not too exquisite, let me explain you that a particular case of this problem with Q, very simple. So I'll start from continuous case, capital L2 on the axis, yes? So yet I take the simplest possible, as we understand, self-adjoint operator. Physicists call it just a momentum. This is just the momentum for free particle. So I take function A, which is 1, plus B. It is just fast decay and smooth function. And I construct this operator, AQ, which is easy to check, just 1, plus the integral operator, which is just convolution. Yeah? And then my cube now is just the interval minus mm of the axis, and then I would like to compute the. Okay, excuse me, I forgot to write what I would like to compute. I'll show on the next. I would like to compute of that things. A lambda, this is operator written here, confined to the interval minus LL. So since A is trace class, this is just Freudholm operator. I would like to compute the determinant of this Freudholm logarithm determinant, but because of this identity, it is trace of log. And we see that it is our case, and we would like to compute the trace of log of A, and the answer given by Mark Katz and Ahiezer, Naum Ilyich Ahiezer, one of my teachers, was the following. So the asymptotic form is like that. It consists of 2 terms. The term proportional to L, to the size of my cube, one-dimensional cube. The second is L independent and quite explicitly written. L is the following. You take this function A, you construct its Fourier transform. Then you take log. I do just little mistakes here, but don't. So A hat is a Fourier transform of that. Then you take log of I, inverse Fourier transform, and this function L, and it is here. So it is a classical result, but it is in fact the second one. I just showed here because it is because of that formula, because I would like to show that how to compute the function of operator. But the first historical result is different. The first historical result was by Haber-Sege who proved in 1915 the leading term, the same construction. You take a function A, you construct the discrete convolution, which an operator in L2Z, then you confine this convolution to the finite discrete interval minus mm, then you take a log that, which is in fact trace of log, in the answer of, and the result by, in fact, two results. Oh, excuse me, Mike. Result by Sege, he found in 1915 the leading term, written here, and after a little of time, he found the second term, which is here, which is L independent, and then, okay, and this is called, these two terms, this asymptotic is called Strong-Segal theorem, and there is a multidimensional analog of this result written here. Already in general case, you take again, according to the schemes that I wrote, you take some physically smooth A and phi, and you use the construction that I described here. Oh, excuse me. This construction, I take the Q, some A, some phi, and thus certain collection of Q's, A's, and phi's on which it was found that in multidimensional case, we have this behavior. The leading term is proportional to the volume, and it is written explicitly, A on P. This is just, I forgot, this is just a Fourier transform of A. The second term proportional to the surface, to area surface, and is a coefficient which is some functional, not simply written, but nevertheless explicitly written functional of these two functions, of test function and the symbol. So we have a lot of things done, and there is enormous literature on the subject about the Sege theorem and related things, and these are it's called usually topless operator. I mentioned not topless but convolution, but there is some subtleties that I don't want to discuss here. So there is a enormous volume, very thick volume of Bocce with Zilberman. There is a book by Simon, the reviews, and there are people worked, which I would like to mention. Among them, Harold Vedem, Estelle Bazar, who is here, and Vladimir Buslaev, to whom we dedicated this conference, and one of a colleague of yours, Sasha Sobolev, who did a lot of, especially in this multidimensional case. Well, and so what the results written here, excuse me, they concern, as I wrote, they are valid for sufficiently smooth A and phi. And what about not so smooth? And there is a very nice example. Okay, first of all, there is so-called, so let me write what is written here. So the experience shows that the Sege formula is, so the leading term, volume term, is rather not insensitive to the smoothness. So it is quite universal. While the subleading term, area sensitive, this area term is sensitive. It depends on the smoothness of A. And the first question about the smoothness, independence of smoothness of A on the form of this asymptotics was raised by Fisher and Hartwig. It was related to the phase transition two-dimensional Ising model. It was raised just in the 60s of last century, and a lot of work was then done by Harold Widom, by Stelbazor, and very many other people. And here is a nice example by Harold Widom of 82. So you take quite smooth as you want test function, but as A, you take just the indicator of a certain interval of the unit circle so it is just function equal 1. Well, your argument belongs to delta in 0 otherwise. And in that case, the Sego-like asymptotics is completely different. The first term is the same. It's easy to show that it is just a particular case of that term. Just a minute of reflections. But the second term is not just order 1. I remind you that in one-dimensional case, since the area is 2 points, the surface is 2 points, area just 2. So the area law in the one-dimensional case just a constant. And here you have log. So it is quite surprising and interesting and not simple to obtain. And there was, again, a lot of work, mostly by Sasha Sobolev and the colleagues of him, that was motivated by precisely the question that I mentioned about entanglement entropy, who found that the general formula is like that. In the case when the symbol is an indicator of certain set. Well, and these are mathematical results. This was the first precursor. And Weidon proving this result, by the way, they made a conjecture about the form of the multidimensional result, and in fact, result by Sobolev and the co-authors just a proof of this conjecture. And this collection of results of interest in itself, in fact, justifies the area law and its violation for translation invariant free fermions. Because I mentioned the term which is not mathematical, translation invariant. Translation invariant because it's about either convolution operator, which depends on the difference of arguments. Therefore, they do not change. The operators commute with the translation in the space. There's a shift operator. You shift all the coordinate by a fixed amount. And that means that your physical system is translation invariant. And another name for such systems is that they are ideal. There are no impurities, there are no imperfections, like ideal crystal. Yeah, just perfect crystal lattice. So, but nowadays there are many quite interesting materials which contains impurities or imperfections. Okay, there are semiconductors, there are metallic glasses, I know, there are okay, other things, quasi-crystals. So the question arises, what will happen if you will work not with, say, convolution operator, Toeplitz operators, etc., but with their analogs for disordered system. This is a name for the substances that you just mentioned. And it turns out that a quite good model, which applies to very many physical, maybe not first importance, but quite interesting physical problems, it is a random Schrodinger operator. Here it is its definition. You work in L2ZD, yes, just on the lattice, and your operator is just the just finite differences of just discrete Laplacian plus multiplication by what? By just by independent, identically distributed, or more generally, shortly correlated random variables. So this is I know I shouldn't explain in St. Petersburg what is a Schrodinger operator, but maybe I just, so it is, everybody knows the continuous Schrodinger operator, but it's just quite natural discrete analogous, which is as well interesting, but technically is much simpler. Well, this is Schrodinger operator, and believe me, it is that it turns out that it is quite, I know, good model to describe a lot of phenomena in these disordered materials. Yes. Well, and now let me just list you several properties which I implicitly I'll be using because I have no time and I know to explain you the proofs the results which I am going to present, but just several properties which may be of certain interest and maybe certain surprise for us. The first property, so your operator is random, but it turns out the spectrum is a closed set on the real axis, is not random, and its support, it could be found as a support in certain measure, again, non-random measure, which known as integrated density of states can be constructed by using a special procedure. Now, let's look in our spectrum. It turns out that the spectrum, that there are intervals on the spectrum, which usually these are intervals adjacent to the spectrum edge, where the spectrum is pure point. So you see immediately a big difference with the case which the audience, I believe, know very much. Let's replace identical, independent, identical distributed random variable by periodic potential. Then the spectrum is absolutely continuous. But if you, instead of periodic potential, which describes ideal crystal, you take IID random variables, which describes just the, two-component alloy of completely disordered. By the way, for example, the alloy of cuprum and zinc. So you have completely different story. You have so there are intervals where the spectrum is pure point, and but eigenvalues of this spectrum is dense in the corresponding intervals. Corresponding eigenfunctions decay exponentially, not the block functions. And what is going on? These intervals exist always, but if random potential is not zero. But if your potential is large enough, allow me not to explain what does it mean, or if you're in one-dimensional case, then the whole spectrum is pure point. So you can't neglect this phenomenon, which is called Anderson localization. So I am going to apply Anderson localization to this, quasi-Sego activity related to the entanglement entropy, but not in ideal quantum computers, but in computers which contains imperfections, because this entanglement entropy is important to use as a certain characteristic of quantum computing. So I am a realist. I assume that my quantum computer is not so, hardware is not so perfect, and this allows me to work on this field. And the first theorem which I would like to show, in fact, this is analog of Sege's theorem for random Schrodinger operator. Yes. So if I would take the potential zero, then it would be a kind of, then the discrete Laplacian, it is just a simple example of convolution operator. I would have the Sege's theorem. But now my potential is random, and the theorem is as follows. If I have a random potential with IID potential with 0 muon, and this is assumption which I will explain why, and the support of because this is random, the values of potential is random variable. So I characterize this random variable by probability distribution. I assume that probability distribution contains, the support contains 0. Then I just write entanglement entropy, and then if temperature is positive, then we have this two-term asymptotic formula for the entropy. The first term, believe me, it is exact analog of the Sego leading term. Yes, excuse, it is one-dimensional case. But the second term is different. It is not constant like Sego case. It is not log like Sego, but with discontinuous simple. It is just, this is a mistake. This should be L to the power plus 1/2, not minus. So the term here, it is not bounded in L. It grows as square root of L, but with random amplitude. And now you have subleading term. So in fact, you can easily recognize here, just being familiar just a bit with probability theory, that is, in fact, it is just a central limit theorem in a spectral context. And so we see that this random case displays a new kind of behavior, not constant, not log, but just square root of L. So we have quite significant fluctuations in this case, and we have no real law. So the entropy is quite big. Now, just as I would like to carry out the little discussion. So we have here, I repeat, we have here smooth symbol, because if temperature is positive, then NF is analytic function, real analytic. H is also real analytic. Everything is analytic, but nevertheless, we have something. We have no. This symbol is unbounded, not like instead of area law, we have just random fluctuation of the volume law, but area law is short term. In fact, it could be found, but I do not discuss it here. The second, I repeat, it's just again, it's just central limit theorem, not hard to prove by using for example, the book written in St. Petersburg. This is nice book by Linik and Ibrahimov about central limit theorem. So you can, in fact, apply the technique developed there, but modulo 1, very serious addition. You have to, all these general central limit theorems, they are proved conditionally, because we do not know much about the process. We assume that the process is such that the variance of the process is positive. And when you apply this general technique, you have to prove yourself that the random process which you are studying is the process which has the positive variance. And it is okay, it's a piece of work. Well, and I would like to say that despite this is a spectral theory in full extent, but you do not use too much the spectral type. What is a spectrum? Absolutely continuous, pure point. You use some general properties in the randomness. Now, okay, I showed you the result about the one-dimensional case, but there are certain results in many cases, in multi-dimensional case, which is in work by Masha Sherbina and myself of 20. Yes. Then, okay, let's come to zero temperature. And let me remind you that at zero temperature, this function is just the indicator. Therefore, this is not smooth case. And here we have the H, which is just x log x, and the P is just a spectral projection. Now we have a spectral theory in full power. So because P on lambda, what is it? P on lambda is a restriction of P, and P is a resolution of identity of my Schrodinger operator taken on the interval minus infinity to E. In mathematical physics jargon, it's called Fermi projection. And it has a lot of application in solid state theory. Well, and we assume now that the Fermi energy, which is characteristic of this is Fermi energy. It belongs to the spectrum, not in the gap, but in the spectrum. And then we compute again the quantity a la Sego, which is in our context is entanglement entropy, but now it is random variable. Therefore, this assertion concerns the expectation of this random variable, simplest possible characteristic. And we find that this random variable behaves, it satisfies the real law. So it behaves like a surface area of my cube. The constant could be found explicitly. The expression is quite involved, but explicit. It is a function of this of the resolution of identity. Excuse me. So, but it is valid for any dimension. But it is you deal with random variable, and you're just able to compute the simplest possible characteristic. Its expectation. It could fluctuate. It could do a lot of things. But just an expectation. Yes. But it turns out that you could do more. So under the same assumption as the previous theorem, we can compute the variance of this random variable. And we find that this variance, oh my God, this is again the mistake, excuse me. There should be minus here. So this variance tends to 0 when L tends to infinity. What does it mean? That means that the entanglement entropy, if your cube is big enough, if your quantum computer is big enough, it is a problem. Now we have the quantum computers at most than 20 qubits are known. So, but it is big enough, then the entropy almost doesn't fluctuate. So it is almost non-random. And physicists call this property self-averaging. Therefore, the expectation, as we used to say in mathematical statistical theory, this is representative. There is no fluctuation. So in fact, this is valid for any typical with probability almost 1, because the variance vanishes. Therefore, probability that you have fluctuations, these fluctuations are small is almost 1. Yes. Okay, and this again proven in this paper by Alex Elbert, myself, and Masha Sherbina. And so, but it concerns any case. So what did we do? We justified in a way the real law for random, so for disordered free fermions. I repeat you that if the fermions are not disordered, in this case, the free fermions, according to Widom in one-dimensional case, is Sasha Sobel in co-authors in multidimensional case, we have log. But here there is no log. I mean, in analog of that formula. Well, we see that the entropy is less. Well, and now what is going in one-dimensional case? Because let me show you, this formula is valid only for dimension 2 and more. And for dimension 2 and more, the variance vanishes for large L. Let's consider dimension 1. One could think that the co-authors, Sasha Elgart, Masha Sherbina, and myself, we were not able to prove something about the case, the dimension 1. Not completely right. We are able to prove, but we proved that in one-dimensional case, the entropy fluctuates unlike the multidimensional case starting from 2. So it fluctuates because we can find that in that case we have this expression. You see, there is no L because in one-dimensional case it is just this is of the order 1, but it fluctuates, and we are able to to write it almost explicitly. So we prove that S plus and S minus are random variables, non-trivial, because we show that the variance is not 0. And then, depending, so we have, it fluctuates depending on interval. So the bigger intervals, the stronger are fluctuations. And so we are more or less done. We have proved that unlike ideal case that entropy is large enough, here the entropy is less. Well, and now the last things, what about the violation of areola? Is it possible in the random case? Okay, we have seen that seems that not possible, but it is not completely correct. It is possible. I have to finish? Yes, I'm finishing. The last thing. So the last result, which is quite recent. So we have proven that there exists a one-dimensional random Schrodinger equation in which potential is not IAD, is not completely random, just a bit of correlations, but quite short correlated potential, for which we are not able to prove the asymptotics, but we found that the entanglement entropy of that system, it is okay. It grows a bit logarithmic. I said a bit because C is quite small constant numerical, but nevertheless it's not 0. Therefore, the conclusion, so it was a recent paper by Peter Miller, myself, and Ruth Schult, and now the conclusion of L. So unlike the convolution operators, where we have absolutely continuous spectrum, random operators with discontinuous symbol lead to area law, and which is not random for D2 and more, and random in D equal 1, and in D equal 1, it could fluctuate. Next, the variance. We believe that the variance. I showed you the bound from above, which shows the variance vanishes, but not as good as one would like to have. We believe that we could do more, refine bounds, and to prove eventually that the variance satisfied that this entanglement entropy satisfied the central limit theorem, be normalized in that way. The mathematical mechanism, which I had no opportunity to discuss because I announced that I would like to make a review. So it is just the list of results, but the proof heavily relates on the most serious feature of random Schrodinger operator, this Anderson localization, in particular exponential decay of eigenfunctions, which implies the same property of spectral projection. And similar result holds for certain almost periodic operators with pure point spectral components. So your quantum computer is not necessarily could contain impurities, even if you use, instead of metal, you use quasi-crystals instead of crystal, you could also have problems with the entropy. Okay, thank you very much. I finished.